This video is about how transformer works. As a triple E student, all we all know that transformer is a static device, which comes under electrical machines subject, and it is a static device. And how does it work? In this video, I am going to explain how does it work. As far as we know, transformer is a static device. That means it does not rotate. Unlike other electrical machines, it's a static device, and it has two windings, and we call as primary and secondary. This is called primary, this is called secondary. And first of all, let's see the construction of a transformer. The construction of a transformer, as far as we know, suppose, let us consider a solenoid or a iron bar, and it is made up of iron simply, and you have a copper wire just wound on it like this. And if you give the supply to this AC, first of all give a DC voltage to this, and current flows, because this wire has a resistance, therefore current flows. This current produces a flux like this, and this flux is constant. This is a constant flux. Suppose we have an iron core like this. This is all iron core. It has like a rectangle shape iron core, and you have a winding here, and it produces a flux. As far as we know, as the flux can pass through air, and flux can pass through the medium. And there is a term called reluctance. The reluctance is the resistance, or it is an obstacle to the flow of flux. For the reluctance of air is high, and reluctance of mediums like a magnetic medium or any other mediums are less than the air. So therefore the always tries to flow through low reluctance path, as, as like a current always like to flow through low resistance path. You have 1 ohm, and this is a 10 ohm. More current flows through suppose 10 amps, for more current flows through this path, that is 1 ohm resistance path. In that way, magnetic flux also, suppose the magnetic flux is coming, this is the reluctance of an iron, this is a medium air. More flux flows through this path because the reluctance of iron is less than reluctance of air. Therefore, in this circuit, now let me erase it. In this circuit, flux tries to flow this path because it has a low reluctance path. It can flow like this, it can flow like this, but it can flow like this also. Therefore, most of the flux flows in this way, like in the iron path, and some flux flows in this way. This is a basic idea about the how transformer works. So now this is the DC one. If you give AC voltage, this is the alternating voltage, and it produces a alternating current because winding has a resistance R which is constant. It produces an alternating current, and the flux, it produces a flux. We know that MMF, which is called Ni. MMF is equal to reluctance of material into flux. Therefore, flux is equal to MMF by reluctance. Reluctance is a material property which is a constant, and MMF is equal to Ni. N is a number of turns and it is a constant, and I is the current. Therefore, flux is proportional to current. As current is like a sinusoidal, it varies, pulsating current, flux is also pulsating like this. Now go back to the transformer construction. And one more thing we have to learn before going into this is induced EMF. There's a term called induced EMF. There are two types of EMF induced in electrical machines. One is the motional EMF, and second one is a transformer EMF. So simply, when first consider for the transformer EMF is minus n d phi by dt. This means when a conductor, like you have a conductor, it is wound like this on iron core. If it cuts, say, suppose the flux is coming like this into this, this flux is alternating. If this flux is alternating, then it can induce a EMF across this conductor. I have a conductor here. This conductor has a EMF induced across it if alternating flux cuts through that conductor. Like it's just a reverse of what we have learned till now. Like we have learned like this. We have a EM voltage, and it has a current flows through it, and it produces a flux. Same way, the reverse happens on the secondary side, on other side, whatever the side you can put here, like wherever it is. If the flux coming in and it cuts conductor, it produces a EMF here, like a vice versa, voltage, current, and flux. Same way, this flux produces an EMF. Like if you put some load here, like resistance connected here, it produces a current. Same way, this is a cycle. Now this is a transformer, typical transformer connection. This is the ideal one, and the transformers, practically transformer construction differs a lot. Now these are the winding connections. This is the secondary winding. V1, that is represented as V2. Otherwise, simply put a load here. We put a load generally. It has a resistance, or simply you can more practically, it has an impedance. Normally, the transformer output terminals having like this, these terminals, and normally let us talk about the distribution transformer. Generally, we see distribution transformers near to our homes, and it has a terminals like this. This is called phase, and this is called neutral. And suppose we have houses like this: house 1, house 2, and in lane 1, and this is a lane 2, house 1, house 2. This is the service mains like this. Typical distribution transformer network like this. So for this is all load. So you can represent like a single component as a ZL, as a ZL load. I'm erasing all this. Let's continue. We have a voltage source V1 and it is connected to the winding of turns N1, and it is wound on a core, iron core. This is the iron core of permeability and mu r, and the other side again winding is wound. It has a turns N2 and the two ends of the winding connected to the load like this. So now simple electrical circuit analysis. Suppose V and winding has a resistance R. So therefore it produces a current I which is equal to V by R. It produces a current and current goes like this. It goes like this, and from the back side it enters like this. Same way it enters like this, and it goes like this. This is the path of current. Now from the right hand thumb rule, you get a flux direction. Like suppose the current flows like this and goes back and enters like this, you can get the flux direction as a upward direction. So therefore it produces a flux. Just reprint with the other color. We already discussed these flux flow. Most of the flux flows through the low reductance path, which is a iron path. So flux direction, and some of the flux flows through the air, and which is not a useful. And why it is not useful, we will see. This is the air gap flux or leakage flux. This is the flux useful one, which flows through the core. As flux produced, this is the alternating voltage, AC voltage, and it produces an alternating current, and which produces a alternating flux. According to the Lenz's law, the induced EMF always opposes its cause. Like suppose an flux has been produced. This flux is alternating. We know the induced EMF formula. V is equal to minus N d phi by dt. So therefore flux is varying and we have N1 turns. EMF is induced across these terminals. This terminals EMF has been induced, which is E1. Which formula? Its formula is minus N1 d phi by dt. This EMF opposes the flux. This flux. That's why it is a negative sign. And after that, this flux flows through the iron path and it cuts these conductors. When alternating flux cuts the conductors, stationary conductors, when alternating flux is alternating, cuts a stationary conductor, an EMF is induced across its conductors. So therefore EMF also induced across these secondary conductors or secondary terminals, which is equal to N2 d phi by dt. Flux is constant throughout the medium, is the flux. Therefore an EMF is induced here also, and you have a, let us consider this is a conductor terminals, and you have a induced EMF E2, and these terminals are connected to the load, and you get a current I2. So you have a EMF here, so if you connect a load, current will conduct, therefore current I2. This is the basic idea about the how transformer works. There are main other terms in this explanation, which is a air gap flux. This is not a useful flux, and this is a working flux. And the directions of EMF. So induced EMF E2 must oppose the flux, must oppose working flux. Working flux is phi, which is a flux through the iron core, So how it oppose the flux? So we know it must the current direction, the flux direction depends upon the current direction, how it flows. If current flowing like this, the flux produces like this. So therefore, this EMF, this secondary one, this secondary terminals must oppose this flux. So then EMF is induced across its terminals. Therefore, in such a way that it produces a current, that current must oppose this flux. Flux is coming like this. The flux produced by this winding must oppose this direction. That means the secondary flux like this. The secondary flux direction should be like this. Therefore, you can get the current direction. If the current goes like this, if the current goes like this, it produces a flux like this, which is the opposite, which is the same direction of working flux. Therefore, we must produce a flux which oppose the working flux. The working flux direction is like this. The secondary flux must oppose this flux. So how you produce this? If current is coming like this, going like this, then you can get the flux direction. If the current is coming like this, then flux produced by this winding is about opposite direction with the working flux. Therefore, current direction for this load is like this. If you wind the winding like this, it is going back side of the iron core, and it is coming front, back side, front. If the winding is like this, current must be like this to oppose the flux. The current coming like this, current direction is like this. Therefore, this is the basic working principle of the transformer, how it works. And the primary voltage induces a secondary current. Simply, there are some important points here. You have iron core, you have two windings, you have a supply. You have only one supply, you get other side of supply. So why transformers are using? Transformers, there are many purposes of transformer. The mainly step down and step up. There are other electrical factors why we need to step down, why we need to step up. Let's consider a distribution transformer around our homes, which are step down transformers. In our household, we need a 220 volt supply, but we don't know the any reason, and it is not our topic right now to discuss about why the transformer. Suppose this is a transformer having some 1 kV input, phase neutral, and why 1 kV, this is the other topic. So therefore, this is stepping down the input voltage to 220 volts, which is a desirable one, which we use on our daily purposes. So this is called step down transformer, which is stepping down the voltage. Same way, there are step up transformer, which steps up the voltage. Suppose we have 220 volts, and we need some other than 220 volts. We need to step up this voltage, which is called step up transformer. And how we calculate this step up and step down? There are two factors, E1, E2 and N1, N2, turns ratio and induced EMF. In a transformer, we have seen the induced EMF across primary terminals is E1 and induced EMF across secondary terminals is E2, and the primary turns N1 and secondary turns N2. The relation between, we can calculate this one, and we know these two because we wound on the transformer core. How many terms we already know, and the supply voltage we know, and we need to calculate the E2. Therefore, E1 by E2 is equal to N1 by N2. And we have, suppose this is the transformers ratio, and we need a 220 volts output, like for a household applications, and we have a some 2200 volts input. This is the output voltage, and transfer how many terms we need to wound on transformer core means there is a reduction in the turn times, so we need to reduce the 10 times, like I wound 100 turns on primary side and this 10 times on second 10 turns on secondary side. Therefore this 10 equal to 10. Therefore we need to wound turns according to the requirement of secondary voltage, and we already know the primary voltage. This is a basic explanation about the transformer. Thank you.